And then usually the people that were supposed to be coming that haven't turned up, we send them a copy of the lecture as well. And then there's further copies of those lectures will be on our new website that's going to be launched next week. So hopefully the information is there for you. I'm going to make a start, and as it says on the screen, hopefully you can all see the screen and the slideshow. I'm Simon Green from Green Building Design. We're mechanical and electrical consultants that generally do a lot of low carbon design, new energy design, dilapidations, general M&E, all round commercial and residential. Personally, I've been in this industry now over 30 years, and Green Building Design has been set up now for just on 20 years. So we're pretty established to what we're doing. Quite honestly, for the last sort of few years, there's been such a focus on reducing carbon and being carbon neutral that a lot of our lectures that we've given previously have been focused on that reducing energy. So this lecture is going to be slightly differently and with a different take, because we're going to focus a little bit more on the well-being and how comfortable are people in buildings, which I sort of feel has possibly been overlooked over the last few years, but with the recent events of the pandemic have come much more into focus. So lost my mouse. Lights on. Okay, so this is a brand new lecture, so forgive me if it's a little bit stilted, because I'm not fully convinced with everything in this subject yet. So really, the first thing is wellness going to be the new sustainability? You know, how do we ensure that our buildings not only protect? Sorry, it's having a bit of a mouse thing. Wellness, is it going to be our new stability and sustainability? You know, how do we ensure that our buildings not only protect the environment, which is clearly what we've been doing as doing low carbon design, but also consider the health of the people that are in it? Now that we're starting to see this gradual return to the offices and buildings, and restrictions being eased and furlough being phased out, you know, employers and landlords are now going to be working really hard to ensure the workspaces are COVID safe. And indeed, you know, we've done many surveys recently looking at what we can do to, you know, have stopping, you know, multiple points being touched down with infrared sensors on the doors that open the doors, so you don't all have hold the same handles and doors that can't be closed or opened without using your hands. You know, you can put purist isotonic covers over, which have batteries in, which emit radiation out that will kill any bugs that are on your hands. And then we've also looked at, you know, obviously encouraging windows to be opened and UVs to put in offices. So there's a lot of people now working towards that, measuring temperatures of people coming in, and obviously getting them to fill out forms. So there's a lot of, you know, easy fixes, easy wins to make things more COVID safe and make people feel the building is a safe place to come into. And what we're going to do in the rest of this lecture is just consider a little bit more about what can we do in the way things are going moving forward. So as human beings, we need to breathe, and so do our buildings. You know, as residents in the buildings exhale, the building will absorb this human-made condensation. It can be absorbed or it can be expelled, depending on the fabric of your building and the ventilation system that's been built into the infrastructure. The building that isn't breathing or is sealed up has no way of getting rid of that internal condensation and moisture, and then obviously then can become damp. And in some of the worst cases, it can also become sickly or even be called, you know, sick building syndromes. So we really need to ensure that the buildings are breathable and are fit for purpose. You know, as humans, we breathe, we move, we talk, we exhale droplets and shed cells throughout all areas of the building. And advances now in science, such as geoscope, have revolutionized our understanding of microphobes, you know, where in fact the average person shells out approximately 37 million microglobes per hour into the surrounding air and surfaces. Now, when you think about that, so that's a lot of microphobes. Some of those are obviously quite harmless and some of those not so. Now, current leading research is really showing that there's going to be a direct correlation between relative humidity levels inside a building and the impact on our health. Now, we've had quite a bit of data coming over from various scientists and doctors in America dominantly that are starting to show that relative humidity levels of between 40 to 60% are the optimum band at protecting and maintaining our own personal health. And really that allows your lungs and your function to function properly. And whilst that's not my field, obviously internal health, I guess what they're looking at there is if it's too dry and then your throat's becoming too dry or your nostrils becoming too dry, you don't have that natural moisture in there to sort of ward off and block off infection. And consequently, if it's too high, I guess it's too wet, and then there's too much moisture around it, then it gives other problems with your health. So I think that's where that band has come from. But so that is figures we're taking from medical research. So for decades now, in the drive to save energy, we've been trying to seal our buildings up, make them very, very airtight, which obviously reduces the need to heat them in the winter, and obviously the need to cool them in the summer. And have we now inadvertently got a situation where we're under-ventilating our buildings in a bid, to increase our energy savings and efficiencies? From now on, we need to start more thinking about, how that building is designed in terms of its internal materials and also its ventilations, and determine which and how many of these microbes will actually survive and become more pragmatic to the users. So our institute, the SIBS guidance, has for long ago talked about the need for humidity control in sensitive areas, and they would typically request it to be 50% plus or minus 5 degrees. 5%, sorry, I beg your pardon. Now, I think that really came around in the sort of the 80s, where we started to introduce computers into offices, and people were experiencing issues with static electricity and more electricity being around in the office compared to the old mechanical typewriters. And therefore, then there was a sort of push to say, to avoid static electricity, the humidity was ideally kept between 45 and 55. And then with the introduction of anti-static carpets and changes of advanced equipment, I feel that humidity may have been left a little bit in the dark. With the current COVID pandemic, SIBS have now started to look much more closely at the dangers of airborne diseases, and that's clearly all firmly in our minds, is how the surfaces are. If we sneezed on something or we've licked ourselves and we've touched the surfaces, we can understand that regular cleaning of those surfaces will inherently stop us picking up those infections. And also, there's been a lot now of information looking at the suspension of aerosols. Every time we talk, cough, sneeze or shout, small amounts of moisture droplets are emitted into the air, which will hang around our environment for a period of time until they either drop to the floor or they're swept away in the ventilation of the building. SIBS are publishing documents at the moment and guidance on how we can continually look to add extra cleaning to that air, which obviously will help reduce any risks of SARS-CoV-2. But as it's all a relatively new virus, there hasn't been much in-depth research other than a general consensus from SIBS, the WHO and SAGE on more ventilation and the flushing through of internal spaces will have a tremendous effect of getting rid of the virus and blowing it away before we actually pick up those aerosol moisture droplets. Now, SIBS have been looking at options of something called displacement ventilation, where we look to bring fresh air into the buildings at low velocities, usually at ground floor level or through the raised floor. And by the natural effect that as hot air rises, we extract at the ceiling level and then try to quickly get any aerosol COVID or other diseases away from the head height level to the top of the ceiling to extract that away. And that does seem to be, fairly common thinking, is that any introduction of fresh air systems should need to be low level and extracted at high level and as quickly as possible. And then also really to start looking at bringing more fresh air in, and with there being a risk then that any COVID laden extract air is being sucked at ceiling level, when it returns to the central plant, we don't then mix it, as is common, to save energy with the fresh air coming in, and then potentially bring COVID spores back down the supply duct and obviously circulate in a sort of a circular motion. So at the moment, we really are concentrating on looking at full fresh air systems in the short term to avoid any risk of extract air bringing harmful pollutants back in, which again, I say, does fly absolutely in the face of saving energy. Where normally we'd be looking to bring, building regulations minimum fresh air in, and obviously, trying to save the heat from that extract air. So, what other things can we do other than the ventilation plant? We've talked about putting ultraviolet type recirculating units in offices, and they're starting to become very common now. Typically, they're about £1,000, and they're the size of a chest, small chest of drawers, and they switch on and they suck air into them. They take them through a series of UV fluorescent lights, those blue lights you see, and then push the air out of the other side of the unit. And that typically does about 65 square meters per unit, not subject to manufacturers. So 6 or 7 people in an area is one of those, and that one gives a very visual impact that we're trying to do what we can to get rid of any COVID air in the environment. If we can stop COVID coming in with testing, then sort of we think we're starting to get half a step there in terms of dealing with the airborne things. So the other thing we're going to start considering is humidity. Now, as I alluded to earlier, there's a lot of American research coming out at the moment, really saying that the humidity band should be in that range of 40% humidity to 60%, which is is a fairly middle of the road air conditioned. And what I've put on here is, and apologies for those who are non-technical, is what's called a psychrometric chart. Now this plots all of the conditions of dry bulb, wet bulb, and also the moisture content or the humidity content of air. And what this is trying to simply show is the red arrow starts outside, say at 0 degrees, and often air at 0 degrees is fully saturated, so it's quite wet and moist, which is quite common in the UK. If we then heat that air up, as we would do in a normal air conditioning unit, you can then see the red line obviously goes from left to right. And by heating that up to, say, 21 degrees, it dries the air out, quite honestly, as we're heating up. And at that point on the psychrometric chart, the humidity of the air coming in would be reduced to 20%. So you can see that heating that air does take quite a lot of the humidity out. Now, again, if we were mixing that with return air from the space, that would likely have a higher humidity because there's people in the space. Those two conditions can mix, and that humidity can rise up, which is where in modern design you would be looking to raise that humidity up on your fresh air. But if we are going to go full fresh air, then there isn't any opportunity to gain sort of free humidity from the extracted air. So in that scenario, we are going to have to add humidified to that space to get that air up. All that air is going to be pretty dry in the space. And certainly if you've got anti-static, if you haven't got anti-static carpets, beg your pardon, then there is that risk of you generating static electricity, and when you touch metal surfaces, you get a shock. So some people may be thinking, oh, humidity, what's this? This is a brand new thing. Well, the answer is no, it's not a brand new thing. And, quality office blocks back in the 70s and 80s would often have humidification built into their air handling units. And typically that would be a steam humidifier. The steam humidifiers were selected, one, because they were relatively cheap to install, relatively straightforward. They didn't take a great deal of space up. You had a box, typically they were called Vapac units. They were silver with a red stripe down the side. Water was put into one side of them, some electrical element heaters in the middle, and inside there was like some bottles, which are a bit like kettles, is probably a good description. And these bottles were constantly boiling. And then obviously at the top of the kettle comes the steam, which then went through a few pipes, goes into a controlled environment inside the AHU. And then after you've heated, you would have you have then added humidity to the air to get to that 50 degrees plus or minus, in line with our SIBS guidance for good office environments back then. Now, what people found was with scale and stuff in our local waters is these bottles become scaled up quite quickly, and depending on the volumes of the use and the hardness of the water, they're quite expensive by the maintenance engineers to change these bottles over. So, after a bit of time, maintenance engineers try to sort of not replace them and let them either fall into disrepair or switch them off. As the cost of electricity has risen something crazy since the 1970s, these things can be pretty expensive to run. If you took 15p a kilowatt hour, and you could very, very well have a 30 kilowatt machine on your roof, it can easily be costing £4.50 an hour. Times that by 12 hours a day, times that by 365 days a year, because they often would run every day. You were looking at potentially thousands and thousands of pounds to run these. So there was a lot of sense to turn them off. And certainly with the introduction of anti-static carpets, then there was a lot of sense there and need that you could get away with it purely from a static point of view. So hopefully that explains a little bit about the humidity. Now, if we're thinking about humidification for the building or for the computers, you can see why it's possibly being phased out. But now, if we're going to consider that we need to be humidifying for the well-being of people in the building, that's a completely different thing to consider. As I said, SIBS would be recommending that the humidity would be 50% plus or minus 5%. And then the lower humidity would be considered below 35%. Now that would be quite dry air, and you could be, if you're in a building with very dry air, at 20% or 30%. You can have people then would potentially have eye irritation, complain of a dry throat, or sometimes even a dry nose. As I said, there's this big risk with low humidity. There's a risk of static electricity, and certainly if parts of the carpet or a lino aren't anti-static, then you can quite easily get, when you touch something metal, a static discharge on your fingers, which isn't very pleasant. Excuse me. So what are the human effects of low levels of humidity? If the humidity in the building then becomes very, very high, and if for whatever reason there's not a lot of heat in the building and we're bringing a lot of air in externally at 90% humidity, you often potentially see condensation can form on cold filters. So if you go back to old houses where there's a lot of fresh air coming in on single glazed windows, you can potentially wake up in the morning and find there's a lot of condensation on the inside of the windows. Now that can be a mixture of high humidity, and therefore it's condensating on the windows, or it could just be that the temperature of those windows is so cold that there is some condensation forming on there as well. But that is an obvious sign when you're getting that the humidity in the space is quite high. Clearly, if it's too humid, you can encourage mold to grow in areas of poor ventilation. Obviously, chemically and then sensitivity emission from that waterborne can be further impeded by the wetness being on varnish and paint, that can allow the paint and the varnish to provide further pollutants to the space. And all this is going to lead basically to a very, very poor quality internal environment. And thinking back to when our mums used to open those windows early in those mornings and throw loads of air in, which was freezing cold, maybe they were doing the right thing by clearing out all of any potential mold and bacteria that's been collected in your bedroom during the night, to blow it through and really try and clear out that bacteria and that mold. Now, as I said, the USA are recommending this 40 to 60% criteria internally for health reasons. And whereas we were on that correct path in the 70s and 80s, most buildings now have really had that humidification switched off, unless it's something very, very specific like a clean room process, or maybe a laboratory which is wanting it, or some parts of hospitals where they're more, they're very, very asking for that level of humidity. Now, back in the 70s, when we perhaps did turn off those humidifiers, there wasn't maybe any major impact, because windows were typically single glazed and very, very leaky of outside air. So, there could very well have been an awful lot of air coming in with good humidity levels, which was obviously drafts from the windows. Now, as we've gone forward with sealing our buildings up, we would very much typically, when we were working out heat losses and heat gains for buildings back in the 80s, have one air change per hour. So if you think of your volume of your room, and the amount of leaking around those windows would be replaced in this volume of air once every hour, and that was pretty common. Modern design now is you'd be hoping you'd be getting that down to much more like 0.2 or even lower. So really, 20% of fresh air is leaking into the buildings. And certainly on a hot house, you're sealing it very much. It could even be, 5% is coming in. So you could be, 20%, a fifth, or even a 5% of fresh air is now coming into buildings that potentially would have been back in the 80s when those decisions were made to reduce those humidity levels. So how can we go forward and maintain safe humidity levels at the same time that we don't end up spending awful lots of money and obviously loads and loads of carbon? So really, without becoming too technical, there are two types of humidity control. There are the steam injection, which we've touched on, which was popularly used in the 70s and 80s, and there's also more of an environmentally friendly one called an adiabatic. So the steam injection, there's a picture there of, if you can imagine that steam gets generated in the pipework, and then through various pressure vessels on the left-hand side, it then gets emitted down into those stainless steel tubes, and then there's a very small amount of vent of steam then gets instructed into the air ducts inside the AHUs, and obviously that's where the steam is then added to the system. I say it'd be common today to see that type of system in hospitals, laboratories, or process plants, where there is a strong requirement for humidification control. But generally in offices now, that you wouldn't at the moment be seeing that, but maybe going forward we do need to rethink this. That sort of direct steam is now would probably almost certainly want to have sterilised water with it. So we then got the cost now of not providing just mains water like we used to do in the 80s and having all that scale problem, but we would have cleaned water, usually RO water or deionised water through a setup plant that actually takes all of the bugs out and takes all of the scale out and any impurities, so that it's very clean water, which again then is another load of equipment, another cleaning process, and another piece of plant to site on the roof, and another piece of plant you've got to buy. But that's sort of how the steam humidification would work. I've just popped in a slide there that kind of shows the other options you've got, where it's basically done in a box, and then there's some pipes that then connect to the AHU. This one here is gas generated, so it's cheaper to run. Obviously, gas is about a quarter of the cost of electricity. And then this one here is a resistive electrical steam generation, so it uses electricity, so that would be like your boiling of the kettle, and then it goes in. And again, we would be recommending this type of thing now would come with air-based, sorry, beg your pardon, RO water, which is very, very clean to stop descaling and help on maintenance. Obviously, some of the problems there with the gas-fired is, are we still going to have gas in a number of years? Is gas going to really be banned from the UK? I know Wales are talking about banning gas in 10 years' time. Obviously, then we've got to get with the flu, and it's a CO2 polluting type product. And that's kind of like how the VAPAT ones would look that we discussed. So the other type of humidification is not as energy hungry. So instead of adding hot steam to our heated air, we can look to use methods of adiabatic cooling. Now, in all of these scenarios, the water at absolutely has to be RO, deionized, protected, so there's no risk of Legionella, and very, very clean using UV filters. And there's various types, but really you can either have a tray of water that sits at the bottom of your air handling unit, and then using vibration and oscillation with pneumatics, it vibrates the water and then causes the water vibration to basically the particles of water to separate. And as the airstream goes across it, it picks up the air that way. Another option is the picture on the right here, where basically we spray our water through this filter medium, and it becomes quite wet. And as the air goes through it, it obviously cools down and picks up the moisture. Unfortunately, all of these processes, because in effect you've heated up the air from outside, getting it to temperature you want, you then put it through an adiabatic type process. I might be the ones that have gone there, but this then causes the air to cool, because in effect you're adding water to it. Excuse me. So we recently fitted one of these adiabatic coolers on a large contact lenses clean room facility, and we had to raise the temperature up to about 35 degrees, and then as it dropped through the adiabatic cooler, again these are all quite large volumes, it dropped to about 18, and then we had to have then another reheater to take that air up from 18 to about 21, and it sort of, the more you heat it up, the more it drops. So you sort of end up doing this sort of seesaw effect that you're trying to put, 55% humidity in once it leaves the humidifier, knowing then that then time you heat it up another 3 or 4 degrees, it's sort of going to drop back to 50%. So it does become quite technical to achieve, but it is able to achieve. But again, you can see there I've heated the air up to 35 from outside. I've then cooled it down to 18 to get the water back into it, and then I've had to heat it up again to lose a bit more humidity to get to where we want. But it can be done. But obviously, we're starting to use quite a bit of energy in doing that. And I say the evaporative humidifier is one where it's the same process, but you're just trying to vibrate the air at the bottom of the AHU, which would then allow it to be absorbed into the air. And then again, that need to be reheated again. And the ultrasonic, basically, there isn't any easy way to get water into air without cooling it down. Now, we were recently asked to do a new design for Spencer House, which is obviously a Grade 2 listed beautiful old ex-palace, and there's a lovely picture there. Now back in 1990, clearly the artifacts were worth millions, and the facade was all listed and absolutely beautiful, as that picture shows. So in 1990, they basically put in close controlled Frankel units with ultrasonic humidification inside each room. And now 30 years on, that's come to the end of its life. So we are now looking to how to replace that. And having done an awful lot of feasibility, researched the market, come up with all new ideas on how we can continue to preserve this beautiful fabric and beautiful furniture. Well, guess what? We've come up with exactly the same solution that we did in 1990. So we're going to start that project in the next few months of carefully replacing all of the water-based systems to provide humidity control. And one of the client's requests was for us to look at refrigerant type technology, because there's obviously a massive worry that the Fankels themselves leak and they've got water, and what sort of damage does the water do? You can imagine a water leak above that beautiful ceiling there, and what would happen. But in terms of the actual providing the performance, we've concluded that that humidification was going to be needed. Now, the only additional thing that we are going to do is we're going to recommend that the water that goes into the humidifiers is RO filtered and UV protected, that just get much better sterilisation and eliminates any risk of possible Legionella or bacteria being created in that environment. So humidity is a big thing to think about for our health. We're now gonna just talk about lighting. Lighting has undergone an enormous change since I started in offices in 1980. In 1980, you had something called a GLS tungsten halogen bulb that provided nice orange light, which resembled what used to be the candles, and usually had task lights, maybe a couple of lights just generally around the space so you could see to get out. And then you had a task light on your desk, and you look where you could do your writing, your reading, or your drawing. Then things started to become a little bit more efficient by changing to fluorescent. And we've been pretty good at designing different things with fluorescent. And then probably about 2, maybe 3 years ago, about 5 or 6 years ago, LED lighting started coming on to the scenes as a potential way that we could replace fluorescent, and that's been developing and going well. And about 2, maybe 3 years ago, the efficiencies and light output from LED lamps passed the efficiencies of fluorescent, and so pretty well from that day on, most new designs now would only really consider LED lighting. And as the technology continues to develop and improve, the efficiencies are coming down. So, it's wonderful for saving energy. It's wonderful for our EPCs to put LED lighting in. Some of the problems that we found, thinking now from a well-being standard, is there are many very, very poor, cheap LED products on the market. And you have to very, very carefully model the light, the color, and in particular the glare. Now the glare is difficult to see, difficult to measure, but if you're in an environment where it's far too glary, and I say without modeling it's difficult to work out, that can lead you to having headaches in those environments, eye strain, fatigue, dizziness. In extreme closes, people say you can have an epileptic fit, although I've never actually heard of that on any of the buildings. But certainly lighting and glare leads to eye strain and headaches. One of the things that it's quite interesting to try is our guidance for the frequency that the control curve for the LEDs works at should really be above 3000 hertz per second. But we have seen some very cheap luminaires from different manufacturers without UK kite marks on that have had their frequency at less than 100. And those two are the ones that tend to be have more issues with glare. And one of the things you can do is you can use your mobile phone, put it onto picture mode, and if you point it at a light, some of the stuff on lower frequencies, you can actually pick up some flashing across your mobile phone by looking at the screens. So if you're looking at going into a new office, you can have a quick check, and if it's flashing on your phone, then it maybe need a little bit more investigation to understand exactly the frequencies that it's working at, and then also the glare that it's working at. Why are people putting in more glary lamps? And I'm afraid it's down to the old cost question again. Manufacturers are able to generate more and more lumens per watt and more light out of each light fitting. So if they can get another 20% light out of each light fitting, you can potentially space the luminaires further apart, and whilst you still achieve your average uniformities because you've got less light providing more energy and more light, that's where the glare can be a problem. So again, to get a proper lighting design done with the correct glare levels could possibly mean you've got to put more lights in of a lower power. But again, we're talking about the well-being of people, and the need there to ensure that that we're not getting too much glare or having that risk with health problems. The other thing, there's been quite a lot of studies done, normally with fluorescent lights, but the same would apply to LED, is you can get the controllers now to have different color temperatures. Now, our bodies are designed, when we used to live in caves, that as the sun rises, the sun is quite orangey, and in time you get to midday, the sun is really above you, very, very strong, and is very bright and quite white. And then in the evening, the sun starts to set, and as it's setting, you you can become more an orangey light again. So there's been a lot of work about looking at the cortisol levels for having what's called daylight controlled luminaires, and the controls can basically start off a little bit more orangey in their colour appearance in the day, and then they can go to white by midday, and then they can dip off to orange later on. Now clearly there's some extra costs for doing that, but really if you've got buildings that doesn't have a lot of windows, or it's got very, very deep areas where the windows are a distant over 10 meters away, then we've seen some massive studies done where certainly if you have a basement with no windows, this type of lighting with daylight sensing, daylight dimming, massively helps people's self-esteem and improves their cortisol levels, and therefore their ability to work harder without becoming fatigued during the day. And then certainly where it's low and zeroed out like that should be really essential, where you're tricking the body that they're seeing a lot of daylight. Obviously, we all need daylight for vitamin D, and those sorts of lights won't give you any vitamin D, but at least they'll stop you becoming fatigued in that area. Moving on to, am I really saying it's low carbon efficiency or well-being? And it generally does seem to matter how we ventilate the building. That's going to have a big factor on the indoor spread of pathogens. And there's mixed and there's displacement ventilation, things that we can use that will also encourage vertical stratification, and their designs therefore that are trying to remove the polluted warm air and get it near the ceiling as quick as we can and get it away from the building, which then would effectively reduce the exposure risk. There's lots around this topic and the ventilation, which method is best. There's pros and cons for each suited to buildings and that. And regardless, the technologies, all these new systems is still going to be assessed over the next coming years. And unfortunately, they are all going to use more energy than just opening the windows. But unfortunately, the climate in the UK means that we can't just have the windows open all year round. So we are going to have to come up with strategies in the winter. And if we want our healthy people, we are going to have to look potentially at strategies to look to humidify the air. Management of these buildings needs to be obviously worked with energy efficiency, but we also strongly need to consider the health and the well-being of the people in there. So I think in short, the answer is yes, we can have both, but it's not without its challenges. I mean, it's very interesting because the next question I'm sure people might be asking is EPCs, energy performance certificates. In the UK, every time you buy and sell a building or you rent a building, you have to have a certificate of energy performance, A being the best, G being the worst, and that should reflect on how much energy the building uses. But it is interesting that looking carefully at the forms that are filled in by the inspectors, there's not one question on there about humidity control. So you could have a building that's actually using an awful lot of energy, having very, very good quality humidity control, and a building next door that's identical with no humidity control, and that is using an awful lot less energy, but they would actually probably have the same EPC. So something else for the government to think about on their EPC website. So by taking certain steps on all of the engineering, there is a subject which really is more for any architects who are on the call is, part of the science that's coming out of America talks about the use of natural materials and surfaces which have good sustainability credentials, and microbes don't tend to like these surfaces much and either don't migrate to them, or if they're on them, they don't tend to survive too long. There's a lot of major scientific studies going on looking at those types of products. So it's not my field at all, and obviously I would advise architects now to start considering looking at these natural products that are good at trying to mitigate the risk of those spread of those pathogens and obviously getting rid of them quicker. There's a lot more work now going on humidity and seeing how that affects health within the building. And I think soon our institute will be looking to really suggest that we do maintain humidity between 40 and 60% to sort of keep our immune systems at our best. and certainly with avoiding anything to do with COVID. I mean, ultimately, if we have healthier buildings, that means healthier people, and the companies that are using them are going to surely be appreciative for that and have less people off sick. But there is an offset against that with some energy consumptions. You know, we think sunlight into buildings is great, and UV can be bring in to eradicate any airborne pathogens, and obviously have a visual impact on there. But ultimately, you know, we've got some challenges ahead and some things to rethink about to get healthier buildings for people in our current COVID criteria. I mean, the future, you know, when you consider that typically when you breathe in air indoors, it can be 5 times more toxic than fresh air. I think that starts bringing into perspective. And I often wonder, houses, you know, modern houses, hop houses that have been really sealed up, to get very little fresh air into them, only the minimum requirements in building regulations, you know, which again is the minimum requirements. You know, I wonder whether that is actually leading to some of our issues with COVID and toxicity. And certainly other countries that have much more nicer or more balanced humidity control and have a better temperature climate, which allow their windows to be open more regularly, you know, they aren't seeing quite the problems with their buildings. Where, you know, there's pictures I've seen where there's hospitals in the jungle and the doctors are there performing, you know, fairly major surgery, and look down at their feet and they've got flip-flops on, dirt and mud, and they're not getting anywhere near the after cross infections that we are in modern hospitals. So I think the humidity is really going to come to fore. Long-term energy implications for cleaning, you know, should remain at our forefront of our minds. Sustainability has to remain high on the agenda as we move forward to zero carbon future. But of course, you know, it could be argued that the wellness of our buildings and our people needs to become the new sustainability that we need to jump on straight away. So I appreciate that's quite a change to the normal thinking, and humidity may be new to people to think about. But you know, we've got a quarter of an hour now to perhaps just open up the floor and have some questions and thoughts on what I've said. So I'm just going to come off of screen sharing, and if anybody wants to come off mute and have a chat to anything we've got to say. If not, I can talk a bit about one of the things that we're doing in our practice through research. Is because of the efficiencies of air source heat pumps, and magically you put 1 kilowatt of electrical energy in and can get 3 to sort of 7, 8 kilowatts of heating or cooling energy into your space, that they are, you know, what's going to be pushed to save energy and reduce carbon emissions. But by their nature, if you have a small one in a car, typically the temperature of the refrigerant makes the heat exchanger on the air go to about 2 degrees. So it's very cold air comes into your car but cools you quickly. When you have a structure, air passing across something at 2 degrees, obviously condensation does form on that heat exchanger, and you drop an awful lot of humidity out. So if it's a hot day and you've got your air conditioning running full blast in your car, if you look under your car, you'll see quite a puddle of water, which is the condensation coming off your heat exchanger. And if you had an experiment and really measured the condition of the air inside your car and the windows are closed, and as you're on your own just breathing, I expect you'll see quite quickly the humidity drop quite low to probably about 20% in your car. That's the heat exchanger. Similarly, if you have an office in cooling mode, it's about 7 degrees usually is the off-call temperature of the heat exchangers. And again, you will drop a lot of humidity in the summer. And again, if you see like little brown spots appear on the ceiling of your office, that's probably from the condensate systems that are there blocked and not working properly and need to be maintained. Now, if you can raise that temperature to about 12 degrees, you don't really get condensation forming, so you're not losing great waves of condensation. Now, for VRF, and this is what we're doing at the moment, and we're looking at the costs of that, we can design air source heat pump with a refrigerant temperature of, in effect, higher temperatures. But what that means is it needs a lot bigger coils to get the amount of energy into the air to supply that room. So you'd end up having to have larger fan coil units in your room, and then having to have larger evaporators outside to deal with the extraction of that heat in the summer mode, or the collection of that heat in the winter mode, because you're trying to take it to lower temperatures, which does have the added advantage that the machine itself then runs a lot more efficiently. And say we're, as a practice, trying to get some hard figures and calculations on that to understand exactly how much extra that costs, what is the paybacks. But we see that that's probably the way we'll solve some of this humidity problem. But do we have any questions? Sorry.
I was going to ask Simon, obviously the ventilation issue is a problem. What about in older, like historic buildings, for example, or listed buildings? Does that cause an even bigger problem?
I think it is. I mean, you could argue, I mean, if you take Spencer House, for example, you know, the advice from the government at the moment is open the windows. Well, you know, to open the windows in London, in that building, the quality of the air from all the cars and the lorries and the buses going by, you know, you could quickly imagine an awful lot of carbon then starting to come into that environment and then sitting on the fabric. So in that environment, it's the worst thing in the world to do. So, you know, we are looking at how we can introduce more ventilation, but it would need to be controlled ventilation that's filtered. And we are looking at what we call HEPA filters, which are very, very high grade particle removing filters that typically you would put into a hospital theatre, so that, you know, we clear every bit of carbon and other sort of dust and crap that's in the outside air in London. So the ventilation that's coming around the space is as clean as it can be. I mean, Spencer House are trying to restrict the number of people in a room at a time and try and have social distancing as a way of stopping the build-up of pollutants. But yeah, I mean, it's a real problem suddenly putting great big steel and galvanized ducts all through old buildings and sucking large volumes of air in and out. Yes, it's not an easy solution, I'm afraid. Do we have any other questions? No? Okay, well, thanks ever so much for all coming, and I hope that was useful. I say, well, we'll get a copy of the video posted to you, and you know, if you want more questions, perhaps give us a ring or drop us an email. And thank you very much. I'll probably see you all again soon. Thanks very much.
Thank you.